we talked about loading and analysis. Okay, so you've created your mathematical model. From that, you decide you have some direction, right? You have a simplification of the real world that you're trying to model in VA or some other program. Okay, you have some intent of this model, right? Like for the homework, we're looking at trying to devise a model where we could design the moment frames, the brace frames, and maybe some of the foundations. We're gonna say ignore the gravity framing, right? Ignore the diaphragms and stuff like that. Like we're not gonna use the results in those kind of localized sense. We're kind of looking at the big frames and the big foundations, big picture sort of, okay? So from there, then you created your model. You want to match all those boundary conditions to that intent and to that mathematical model to represent it the best we can. Okay. Then we have to load that model once we feel good about the boundary conditions. So we start loading it based on, again, the intent of the model and what we're trying to get out of the model. That one seems really close today. No? Oh, okay, that's probably it. So we load it, okay? Then we can analyze it, okay? And hopefully things run, fingers crossed, but if they don't, then we have to start troubleshooting our model, right? And this happens a lot, where we go through all of this effort, we put in everything that we think will work, and in the end, it just comes out with error messages, right? We talked a little bit about error messages that you don't want to overlook them. Okay, so when we troubleshoot a model, and I think all of this I have written, I don't think there's anything you need to write down. Okay, we're going to try and speed this up a little bit. So as the models grow in size and complexity, so does the chance elements or boundary conditions will be misrepresented, leading to instability or inaccurate results, right? Okay. Our little frame that you have for the homework is a small model, very small model, okay? You think of that compared to the engineering building or rendezvous dining pavilion, things like that. Those are very large models, thousands of elements, thousands of plates, thousands of nodes, thousands of degrees of freedom, right? I think Brandon said that there's already 5,000 degrees of freedom or 5,000 elements?
That's the size of the matrix.
Oh, okay, 5,000 by 5,000, so 5,000 degrees of freedom, okay? So that, I mean, that doesn't take very long, and VA is having to deal with 5,000 degrees of freedom, right? And so there's support both on the industry side and then on the, what I'd say, experience side, just from doing this. On the industry side, we have internal model checks, and those checks can point out possible issues, okay? Programs vary in the way that they do this, okay? Their level and type of support, okay? I'm just gonna talk about the experiences that I've had with how really BA supports you during this process of figuring out what's going on. Obviously, they have a lot of help files and videos with modeling topics. Okay, don't overlook this. When you're figuring out how to use a program, okay, tutorial videos are incredibly powerful, okay? Making sure that you're doing this, you're educated when you're doing this, because garbage in is garbage out. Unfortunately, garbage in and getting garbage out could be like a life safety issue, right? Could be a big deal, right? So some items to watch for, okay, from the software is a statics check, right? What does a statics check do? Anybody know a statics check? Anybody use the statics check in BA? Jock, look at you, stand out today.
You used it too.
Oh, you did, Elias? I didn't see it.
This morning, Jock was a lot. It was helping me out a little bit.
Oh, okay, so we get cheating going on, huh?
No, just showing me how to use statics check.
See if it'll turn on here.
But I don't really know what that means still, honestly.
Well, that's why you're here. That's why I'm here. All right. So, you got this model, right? Oh, come on, baby. We got our model view. We've run the results. We've got this nice status bar. We want to make sure, maybe take an eye and look at this. Make sure that everything is adequate. We'll talk about some of the things that will come up. All right. But in this results view, as long as you don't click anything on this results side on the project manager, there's a section that says static check. Okay? It goes through and it checks in each load case the applied forces in which direction, global direction here. Right? Moments and forces. So in this case, if I'm in the dead load case, right? And I'm in the Y forces, maybe we'll start with X forces, right? 0, 0. Okay? It's a very quick way of coming through here and looking at a model and saying, all right, if I have just vertical dead load, then my assumption is that I shouldn't have any lateral forces, right? And so if all my forces are sourced in the Y direction, then I shouldn't have any forces in that direction, right? Really quick way of finding out whether or not you loaded this in the wrong direction or accidentally put a wind load in the dead load case, right? Or earthquake load in the dead load case, all right? Applied versus reactions, okay? Gives you the balance, right? What's the difference and what's that percent error? What is VA doing here? Well, it is taking the applied loads on the deformed geometry while looking at reactions of the undeformed geometry. So what is this? Reactions are based on the undeformed geometry. The applied is based on the deformed geometry. So it solves the problem, then it runs back and it applies the forces. Okay, we said that VA is not iterative, and it's not. But what it does here is it's just checking. It gives you an indication of the relative magnitude of displacements, right? If your model displaces a long ways, it's essentially giving you, okay, you might have some P delta issues, okay? You might have quite a bit of displacements, right? So it gives you a feel for displacements. It's not necessarily a direct indicator of an instability issue, right? But it gives us some relative sense of the overall displacements, right? And whether or not P delta is going to be affected.
You're saying it applies all your applied forces to the deformed shape?
Yes, it's
So like
applied loads on the deformed geometry while looking at reactions of the undeformed geometry.
So like deformed, it would deform in the way as if you doubled your applied loads. Like the loads are applied, it deforms this amount, and then you apply them again to that, or like, ground.
It is, let's see if it'll do it again. Let's see if we can get their description. Shows the sum of forces and reaction in this direction for moments. Maybe it doesn't show it here. I'll have to go dig into between the applied loads and the reactions in the direction shown. Normally this should be 0 or close to 0 and could indicate nonlinear behavior of a mechanism, large displacements. The way that it's the applied loads on the deformed geometry while looking at reactions of the undeformed geometry. So I think it's saying, it's essentially allowing you to look at how much are the displacements, right? The movement of the model affecting the overall reactions, the statics of the model. Does that make sense? And it gives you this relative, like if there was a huge difference here, then that would mean that the displacement of the model is going to affect the statics of the model, right? It's moving. And so in some cases, it might not be an indicator of instability, right? Because you might have a load case or a load source, right? Dead load's one thing, but if you had, if you had a load case where you have dead plus wind, right? Like the 0.6 dead plus 0.6 wind, or 0.9 dead plus wind, right? And so you actually get a model that's displaced, like if I looked at this one here, should have those in here. Maybe the model's not displacing enough. You might end up getting some change in the applied force versus the reactions.
That's what I'm like dealing with right now. I have like a statics imbalance. That's what I'm trying to fix.
The help file is incredibly helpful, like just reading the section on the statics check,
Sure.
right? Because it's essentially saying, okay, if the model stays put and it doesn't displace, what are the applied, it's really giving you the applied loads, right? And then it's saying, okay, now we're gonna let this building displace, and now we're putting the forces on it. What are those applied forces? And gives you a difference between the two. And so there might be a difference here. And yes, it does, it'll poke up an error over there saying that you might have a statics imbalance, right? But very helpful if you were looking at, right? Service level, well, that wouldn't be service level, right? Like service level live loads on your structure, you can then say, all right, my reactions are 67.653 in the vertical sense, right? Based on my hand calculations, I should be really close to that, right? Based on the areas.
Why are your beams displacing, why are those one beams displacing so much more than the others?
It's a relative displacement thing, right? So they're just showing,
It's just
it, yes, it's a magnification of the, should give us the displacement.
Scale factor.
Yeah, right here, right? But this scale amplification is all relative based on the displacements that are in this model to begin with, right? They make it so you can see it in the first place, and then you're gonna move it from there, right? So it might look like a lot. Those joists are probably, right, 12 by 22s I think I had you guys use. Oh, wow, 26s. Big heavy. All right, so that is statics check. Oh, it's still recording. Perfect. So as I mentioned, provides a feel for displacements, not necessarily direct indicator of instability or an issue. Sometimes you might have some displacements and might have some small amounts of a statics imbalance. Not necessarily, modeling based on small displacements, right? So if that imbalance gets large, then that gives VA a means of saying, hey, we probably, or you might have a problem, okay? Probably have a problem, might have a problem. Another thing that VA does, you might have seen in your model, is member stresses. If stress exceeds the material yield, right? Every member has a material property to it, okay? So in that material property, I'm like so roasted right now. It doesn't go any further.
Can you put that shade light down though?
Oh my God. How far do you want it?
I'm being blinded, that's all.
That's all right. Is that enough? Was it better down here? Tell me when. I gotta close the whole thing, seriously? Fuck.
It's very bright.
Okay, that's fine. Jesus.
Oh, I feel so much more engaged.
Yeah, right. All right.
So for the,
Ma'am.
I have a question.
Yes.
So for the results, there's like a red for the status and then a yellow and then just like the normal tan.
Yep. It's
color.
just different levels. I don't know exactly, but I know I'm pretty sure that the red is more based on the actual modeling analysis, like instability with the finite element portion of the analysis. I think the yellow is more on the like inaccuracies in maybe further down the road of like the design tab when you're actually taking those things and designing them. Like if you had,
Statics imbalance is yellow,
yeah, so it might be like, hey, we were able to get through the analysis like finite element wise, we got a solution, but now there might be some things you might want to consider. Like one of them would be like member stresses. So if your stress in your member, obviously VA is calculating displacements, right, and rotations, and from that we can get stresses. And from those stresses, if we picked A992 with a yield of 50 and all of a sudden the model's coming up and it's saying, well, the yield or the stress in this member is 60, right? We're assuming a linear elastic model, and now we're in the non-linear portion of the stress strain response of this material. They want to let you know that, right? And so that's one thing with members. So if stress exceeds material yield, again, not necessarily direct indicator of a model issue, but our modeling is all based on this linear elastic behavior, so there might be an issue, right? You might want to consider that. I'm going to review that. Right? Node fixity. Well, models can tell if your model has rigid body modes, right? If a mode can just fly off in space, it's not fixed well enough, well, they can isolate that node, right? If it doesn't have enough fixity to it, and it's going to tell you that. And VA will say, hey, we've got this node, it's node 004. It's not attached to anything, right? Okay. Models can tell if the node is not connected, will help get model going, but might be stable yet not represent the mathematical model, right? So you might go out there and say delete the node, or you might go out there and apply boundary conditions to it. But again, you need to be methodical in that node and think about, even though it might be able to fly off into space, right? When you attach it back to the model, you got to think about how does that represent the mathematical model. Yes.
If you have like a pin connection and you have a member framing into it, would it be redundant to release that member framing into that pin if it's already pinned in place?
Yeah, I mean, if you do that and that node doesn't have any other members attached to it,
Then
right?
it'd
We've
be
talked about that.
yeah.
Yeah, then it'd be unstable. So you, like, one of those members framing into that node will have to be able to actually hold the node.
But I guess then there's nothing wrong with still releasing it or having it rigid. That's not gonna affect the results. Like, let's say if that node is fixed, then you have another member coming in to that pin connection.
Yeah, I mean, if you had everything coming in and you released all the members framing into that node, and then you decided to fix the node to keep the stability, then that node shouldn't get any moment from any of those members framing into it.
Right.
And it would represent essentially a pin. Which would be a weird way to do it, but yeah.
Well, I guess that's not.
It'd be an interesting way to do it, okay? It'd be a creative way to do it.
Well, that's not what I'm saying. I'm just like a bunch of members framing into a pin connection.
Yep.
It's already pinned. It's like the node itself is pinned. So releasing the members framing into it would be redundant, right? To like not allow moment to transfer into that node.
Yeah. Would be redundant.
No, because the each one of the elements is fixed to that node.
Right.
It's just the node itself, it has no external like fixity to it. So if you had a bunch of members framing into a node, the node might be pinned, but all those members then are fixed at their point of contact with that node. So if that node rotates, all the members around it have to rotate with that node, right? Because if like one member has a bending moment on it, it's gonna try and bend it down. Well, if all the other members are connected to that node, then that node's gonna rotate. It's gonna have no outside like fixity to hold that node in place because it's pinned,
Yeah.
right? It's not gonna translate, but it's gonna be able to rotate, and it's gonna impose those rotations on all the members attached to it. So that's why you wanna release
That
it.
makes sense.
Is that? Alright. Displacement relative magnitudes. Programs can assess level of displacement and warrant of concern. So VA will do this. It'll say like obviously it knows the locations of all the nodes in your structure, and it knows there's members connected to it, it knows where all the members are. So I'm pretty sure we could ask Adam, I'm gonna try and get him to come in next week, but it takes like one of the like global extents of your model. So like with our stair tower, for instance, right? It had a height to it based on the extents of the node, the furthest node from, in the Y direction, furthest nodes in the X and then the Z direction. And it can figure out what those like overall like global dimensions of your model is, or the extent of your model. And then it says, okay, in order to have small displacements, I might, consider small displacements some percentage or portion of that overall extent of the model, right? So it could say if we have a 40 by 40 by 40 block building, right? If I have 0.01%, if I have displacements that are greater than 0.01% of that, then we probably might have problems. And they're gonna tell you that, right? So if you get a displacement of like 4 inches or something like that, or 2.5 inches, it's gonna say, hey, you're kind of exceeding the overall extent of this like model you have, and we would probably consider those as excessive displacements, and it's gonna tell you that, okay? And so it can be very helpful to kind of quantify what those displacements are, okay? It'll tell you. So those are some of the model features, right? Program features in order to troubleshoot and try and work through. Obviously you guys have done a lot of that already, right? In the homework, hopefully. And going through the yellow and the reds, and it says, okay, this isn't connected to anything, or you have rigid body modes, or your material stresses are too high, or your statics check is fucked up, right? All those things, right? It goes through each one of those. And so then the other part of it is experience methods, right? When we get past that and things are still not running and it doesn't seem like you are having a pinpoint location based on the model's help, okay? Then it just comes down to doing it over and over and over again for hours on end, right? So over time, you will begin to develop your own techniques, processes for modeling and working through problems in your analysis, right? And this just takes time, honestly. And based on being there in a firm with other people, hopefully, that have been in your situation potentially, maybe modeled a similar building or similar structure, or tried to design a certain component out of a building, right? They've hopefully been there and done that, and they can help you troubleshoot, okay? These are some of the methods that I've used in the past to debug models. The worst models I've ever had to like troubleshoot and debug are the ones that we used where we would take a Revit model and try and export it to VA. Okay, like a large Revit model, and then everything is fucked up. It's just, there's nodes everywhere, things aren't aligned right, members aren't connected to things, nodes are flying out in space, right? It's just, and there's thousands of them, and you didn't really establish where things were originally. So based on having to beat my head against the wall so many times, we've just decided, I think I mentioned this, right? Not use that integration method and just start from scratch and build our own model, okay? And so it takes time to do this. First step would be to try and be, well, I guess first concept here is always to try and be systematic and not reactive, right? Don't just keep chasing the little error messages that VA sends you, right? 'Cause it might just send you all over the place, and pretty soon you might, maybe you're gonna freak out, okay? 'Cause it's just like never gonna just work right, okay? And so you gotta just be methodical, be systematic, right? And step through it as if you were just starting at the beginning and working your way through, right? So don't just chase a program provided errors, as there can be many, or they can be misleading, right? Start with your nodes. That's where I always start. You want to start and be systematic, right? So if you start at the top level and you work your way down, bottom level and work your way up, okay? One cool feature in VA, I'm going to show you because the people that I have showed so far have been like, whoa, you can do that? All right, so in the model view, there's this little cut feature in the project manager. It'll work. Oh, it's got to adjust to the screen size. All right, if I was going to, well, let me go back here, model filter. I want to show the nodes finally. So I got all my nodes here, right? Got all my plates, I could turn all my members off. If I wanted to cut and I wanted to look at all the nodes at the ground floor, right? I can go through and I can cut my model so that it only shows the bottom nodes. So you can be very methodical, and VA created all these automatically. It's saying, okay, I've got a bunch of nodes on this plane in the X direction, so I'm gonna generate a plane. You can do your own cut volumes, okay? If you wanted to look at, say, a certain couple stories of your structure, or maybe it's just one quadrant of your building, right, that you start designing, you can select all of those things, you can create a volume over that, and then you can just cut that out. So if you want to just like isolate that part of the building, it makes it really easy to do. Okay? So this allows you to be very methodical, right, with respect to nodes, or if I walked up to the next height, right, and I did model filter and I wanted to look at members. Right, now I have all the members on the second story. Okay? Pretty nice. So cut planes, help you do some of that. So I usually start with nodes, top down, end to end, up to you, just be systematic. Then I jump into members, right? Top down, end to end. What am I going to look for? Well, I'm going to start isolating sizes, types, right? Is it a joist? Is it a girder? Okay. Is it a brace? Right. Then I'm going to jump into plates. Okay. Plates is usually where I end last. I start at the top. Okay. End to end, whatever that makes sense based on the structure you're designing. I'm going to start with, okay, maybe I have 5 inches of concrete over here. Then I have 9 inches of concrete over here. Maybe I have a steel plate shear wall over here. Okay. So I'm going to start by looking at the thicknesses and material types, right? So I'm going to go over, I'm going to look at, okay, everything that I have, that the diaphragm is 5 inches of concrete, I want to make sure that it's 5 inches of concrete, right? It's F prime C of 4,000 KSI, right, or PSI, right? all those things, just kind of work through it systematically. What also helps a lot is the, I think you guys probably seen this one already. That find tool that we talked about. Right, in the bottom of the model view. Down here is the find tool. It's still going.
Do you know if I did that guy down there? It's not already down there? Or is it always down there?
It should always be down there. Is yours not down there?
I've had times where it doesn't show up and I can't get it to show up.
Against that thing that's expired.
What's that?
Just on the first tab on the left.
First tab on the left?
Or just-
This? I think that brings up like a search box. I'm not sure. It might be in. Really? It's never shown up sometimes?
I think you have to like, I think
Is there a pin right there?
yeah,
Oh, this one right here?
yeah. Well, it's,
Let's auto hide.
so if you click that, I think it like.
Oh,
that
I
should
didn't
be
see
your-
you did that.
Yes, get rid of it.
Oh, now you're really.
It's on.
Find tool right there.
Oh.
I've had it where it like shows the.
Pin that thing. Boom! Did it! Yeah, that's why I'm up here and you guys are down there. Maybe I should have made the homework easier. So the find tool is really helpful in this regard, right? Because it's separating all of your member elements and it gives you all of the materials and you can select, right? You can sort all of your members by the material that you're in, and then you can select those members, and then it's going to highlight all those members in your model, right? So if you wanted all of the members, say at a given cut, to be that material, you could sort this by A992. You could select all the members, and then you could go and select the cut you want. You could step through top to bottom of your building and make sure that each one of those cuts, all of the members are highlighted. You would know they're all A992, right? Nodes, right? Gives you nodal information, where it's located, what types of supports it has. So if you have a lot of members that are pinned, right, it's gonna show you that, right, in this case, these are all fixed, right, rotation and displacements. No, those are pinned, rotation and X direction. No, those are moment break or bases. So just very, very helpful. It also gives you member loads. It tells you where they're at. Okay? You can go through and figure out the service cases. Very helpful tool, okay? Back and forth, back and forth. If the model still isn't running, and this might happen with big models, right? You think you've gone through and you've found everything, you've gone through it twice, 3 times, okay, maybe 6 times. You spent 3 days on it, okay? You leave the office at 1 in the morning, just completely demoralized, right? You still don't have the model running. Scared now, Madison?
Oh my gosh.
Right? You're just like super pissed off, okay? You can start and kind of do some of these, right? Can do in steps, right? 1 floor or 1 diaphragm, right? You can go through and just, in one of those cuts, just fix all the all the nodes, right, on a floor level. And if it runs, you're like, oh shit, I've isolated to the 1 point, right? Or I've gone through and I've fixed all the nodes and just kind of started over. Just fixed all the nodes in the model, okay? And then start it over. This might give you, I mean, it might highlight a node issue or an element issue, right? You may have had some rigid body mode. You may have had some release problem where you over-released all the members into a node, and now that it has fixity at the node, it will run, okay? And so you can methodically go back through systematically. And you can remove all member releases. Sometimes that'll help, and then just start over, okay? And go through, or do all the member releases, right, at 1 floor or diaphragm level, right? Or 1 grid line, work your way through. Just see if you can isolate it and get the thing to run. All the plate releases, you can do that. It could be a release issue on your plates. Membrane action, if you happen to think that you wouldn't have any out of plane loading in your diaphragm, but then some reason, some loading scenario, you added a load that you shouldn't have, okay, or something's framing in there that shouldn't be. Maybe you have a member and you never supported the node inside of a plate, so now the plate has to support it, but then that plate you said was membrane, so it can't support out of plane loading, okay. So then you go through and you can remove membrane action, and now all of a sudden you might be able to get some solutions to this. Hopefully, if you do it small enough steps, right? Be again systematic. You can do the entire model, and I've done that before, but sometimes it's nicer just to go through those cut views and select all the nodes and fix them and see if it runs, right? Just boom, runs, okay, back up, just undo, right? Go to the next one, right? If you find the problem, then you can go through and be a little more detailed oriented and try and pinpoint where it's at, okay? The model still isn't run. Simplify it, right? If it's just, maybe it's just too big, okay? Too complex, okay? You might have, one of the biggest ones that I had a problem with was the fact that my nodal tolerance was off. And so as much as the nodes looked like they were connected, right? Or it looked like there was one node, but in reality there were two. And then VA has this thing, it does nodal tolerances. So if your nodes are within a certain distance, okay, it's gonna smash them together. And so it wouldn't smash them together, but they were close enough that I couldn't perceive it in the 3D model, right? You chase that for hours, right?
Why would you have something with that close together?
It's from the Revit thing where it kicked it out from Revit.
Well, why wouldn't you just make your nodal tolerance like a foot?
So I didn't know about that whole thing, right? Now I'm telling you that it was nodal tolerance because I knew what the problem was. But before that, I did not know, right? There's a little thing in VA that says it's like, I think it's 0.0625 or something. It's like a small amount. But in Revit, as I mentioned, the analytical model or their mathematical model is based on the center line of members. So if you have a W18 by 35 and then it frames into a W18 by 40, those things are a little bit deeper, right? And so the real center line of that member is a little bit lower than the one that's coming in next to it. And if Revit doesn't assume that they connect, then it's gonna create another node at the end of this member when it kicks it to VA. And that's what happened all over the place.
So what version of V8 are you running?
This is 19.
Why can I still not find the offset box? For my plates?
can't
I asked him,
send
he
education.
couldn't find it either.
So you offset the member, not the plates.
Oh, that's why.
Yeah,
Okay. There it is.
you offset the member, not the plates. So if it's still not running, simplify it, right? Usually the structures that we deal with, a lot of times, if you're in the office building, even like with residential, okay, if you were to make a VA model with it, right? It's pretty segmented and mirrored and copied over, right? So you can start with maybe a small corner of it, model it, and then just copy it over, right? We can remove degrees of freedom, right? Just simplifying it, right? And then finally you can change jobs, right? You can always change jobs. Right? But hopefully you won't get to that point, all right? You'll be able to get this model running, and once we get the model running, we feel good about it running. We get results from that model. All right, these are the fruits of our labor. This is where hopefully it all made sense, and it made sense to put it in VA and analyze it, not just try and make some other simplifications and do it by hand, right? The intent here is to use this as a tool to simplify things and gain efficiencies and do it faster, right? So software packages provide all sorts of results depending on post-processing capabilities, right? So these are some of VA's abilities with respect to providing results to you. I mean, they'll bring, I've never dealt with it before, but like bill of materials, right? VA will itemize all the materials within the model, right? All the members, sizes, lengths, and breaks down all the quantities for you. That's really helpful if you're a contractor, right? All the model summary and results checks and things like that, right? It gives you the ability to report that. Obviously, you can use that as a valuable tool when you're developing your model in the first place. We've got your structure tables, right? Materials, member crossing, nodes, where are your nodes at, where are your plates at? Again, very valuable for when you're trying to get your model running. Load tables, right? Member loads, uniform. Obviously, I took this from our stair model. Sometimes depending on what things you have in your model or don't have, this available tables will get bigger or smaller, right? There's other things out there. So you get stresses and forces, obviously, and displacements. A lot of stuff. They also provide a really powerful, like a graphic interface, right? So we can actually see the behavior of our model, right? That's the whole name behind visual analysis. That's why it came this way, or that's why they came up with the name. Was based on the fact that Dan Van Lushen, and I think it was a grad student at the time, they like modeled a portal frame and they actually got it to show what the displacements were, and then they decided to name it visual analysis from there, and that's where it came from. Okay. This is incredibly powerful, but you need to remember, like with plates, the coordinate system for our results, right? We had those moments, and those moments were not about an axis, they were about the face of the plate, right? Based on those local coordinates. And so the results that we get out, we can tell it all sorts of crazy stuff, like what plane are we on, right? Are we on the top plane? Are we on the mid plane? Are we on the bottom plane, right? Obviously, with some of the bending, we might not have stress at the mid plane, so if we wanted to look at stresses, we might look at the top plane and the bottom plane, okay? Gives us all sorts of shaded stuff. You can take these bars, show you this, all right? You take these bars, you can slide these bars down. You can say, okay, anything beyond a certain stress, I want it to turn into gray, and it'll gray it out in the graphic view, right? So you can look at a whole model and say, all right, all of these areas of our diaphragm or all of these areas of the plate are excessive stress, right? Right, we're gonna have to do something about them. We can provide, if you click on this, you can provide like ranges and actually input what those ranges are, okay? We can change this from a gradual scale to actually have ribbons. So you get like 5 different color bands or 10 different color bands, right, between those different values, right? And you can do all sorts of stuff, right? Stresses, displacements. You do plate results, obviously. Member results, same thing. You can show the shear diagram. You can show the shear stresses. Incredibly powerful. Can also be a very powerful tool for troubleshooting as well. Right. Helps us convey information, right? Internally and externally to your firm. Okay. And the way that we report these items is going to change depending on what type of member we're designing, right? If it's a beam or a slab or a brace or a diaphragm, all of those things affect, right, which tables we really care about, okay? Or if we were going to show it in a graphic sense, what we care about also. The graphic sense is really powerful when you do like concrete foundation walls or foundations or tanks. It really shows you and highlights kind of the extent of very large stress concentrations, right? Or very large forces that are happening. And a lot of times that happens at discontinuities. If you had like a point load landing on a single node, obviously, VA is taking that on the finite element side, and it's one single node that gets a huge point load to it, right? And so sometimes that force can be significant, and it's going to try and impose a huge displacement at one given node, and so you might have a big stress concentration, and that's going to then dissipate out. All right, so we have these results, and we have all sorts of results that we can go through. We don't have any errors. We feel good about our boundary conditions. We feel good about the fact that we're trying to model the mathematical model. When we're modeling it in such a way, we have some intent, right? Something we're designing based on this, and we need to validate it, right? In the homework, I asked you to do some validation. Right? The intent of using VA, though, is we're using it for very complex structures, right? Things that are very indeterminate, things that we could not analyze by hand very easily, right? So that's like, well, how the hell do we validate it if it's so complex and so indeterminate that we couldn't do it by hand anyway, right? Well, then we just simplify our validation. Again, we're just trying to validate or feel good about the results that we're getting out of it, okay? Like in the homework, I asked you to look at, the vertical forces, right, or the service level applied forces, okay, and validate those by hand, right, calculating by hand. Very easy to do. You figure out all the applied loads based on areas and everything like that globally, and then you can go in VA and make sure that you have imposed all of the dead load or all of the live load or snow load that you assume that you would, right? So at least you can validate, okay, all the loading I'm putting into this makes sense, okay? You could go to a member, right? A member that you've done simply supported, and you put a uniform load on it, and you could validate that individual member's deflection, individual member's internal forces, right? Moments, shears, and everything for that individual member, right? At the, say, the local level, the micro level, and you use all of these kind of little pieces of validation to validate the entire model as a whole. Does that make sense? Because you can't really say, all right, I'm loading this 4-story stairwell frame, and I'm putting all these different loads on it, all these different load combinations on it, and I know by hand that the deflection of the top right corner node is 4 inches, right? It's like you're just not going to be able to do that. So you go through and you simplify your validation. It's still critical, right? Still allowing you to make sure, because it could run, obviously when you get it running, the amount of dead load you put on it, you could vary that fairly significantly and still get results and just be unaware of the fact that you made the mistake of moving 1 decimal point in one of your applied dead loads or live loads. The model runs, everything's doing great, but overall, that amount of load you missed, right? You missed the target on that just because you moved a decimal, right? Or someone else was working in the model and they like to use kips and inches and you like to use kips and feet, right? Or kips and pounds and feet. And so then they went in the model, they were looking at something, they changed the units, saved that model, and then you went out to go design some other member in there, and it's at inches and pounds, okay? And you're like, and you just use the thing assuming that it's kips, and then, you know, you design something inadequate, right? Or you apply a load and you thought it was in kips, but it was in pounds, okay? So we must feel confident in our results, and that's what validation is all about. You do not want to just blindly use the results. You want to be able to validate them to some level, right? We need to make some educated comparisons to feel good about our results, and that's where we make some simplifications, possible comparisons, right? Displacements, relative and or absolute, right? If we were looking at, say, one of the joists in our stair model, right? Based on a provided uniform load, we could validate the deflection of that individual joist element, right? Make sure that VA is doing that appropriately. Okay. We could do overall forces, right? Reactions is a big one. That statics checks, applied loads, you can figure that out. Internal forces, again, if you had that uniformly distributed beam, you could figure out what those internal forces are. Yes, James?
What would be the easiest way to check story shear? Just look at like VY of all the beams, or?
I mean, that would be giving you the answer to the homework.
Not the answer. The answer is you have to still do the check.
Yeah. Well, I mean, I would say
VA.
think about it from a mechanics standpoint and what you're trying to get out of it, right? You're looking at the story shear, hopefully the definitions I sent you, because I think there was some confusion, right?
I'm just
on what
asking,
that was.
that cut tool you were showing us, can that help with that, or should you just look at like the overall
It
results?
could help with that. Yeah, it definitely could. It could highlight a certain area of the structure that you'd be interested in knowing what the shears are. Right? So internal forces, I mean, that's why I asked you in the homework to do story shears, is that's a very good simplified approach to make sure that, say, at some story level, the applied loads at everything above it are what you think that they should be as that force is moving down, okay? If you lose some of it, obviously you might have a reaction or some sort of resistance to translation, right? Maybe you fixed a node in translation that you shouldn't have, and all of a sudden now you pulled out most of that load, okay, that you thought was going to be there. Member forces, again, another one. Stresses, relative and or absolute, okay. Big thing here is we can always start with a simple model and then add complexity to it, okay? Like we started with the last homework with the cantilever, right? We could absolutely look at what the displacement was of that cantilever at the top, and we could verify that directly with B, right? So maybe you look at if you had a building and it's on a very like regular grid system, which a lot of multi-story office buildings are, maybe it's 25 foot or 30 by 30 grids. Okay, you pull out one of those grids and then you start just validating a model just on that single grid. And then you can copy that through and then do some other validation as you go through. So you can feel really good about that simple model and then extend it off. Okay. As our indeterminacy increases, exact computational validation becomes more difficult. Right? Obviously, that's why we use computers. And so we have to simplify our validation efforts. Okay. And convergence, last part of this. Wow, we're cruising. I love this shit. Aaron, you tired today?
Me?
Yeah.
No?
Okay.
Are you?
I am tired today. I'm a little tired today. I just heard you've been working a lot.
Well, I left the mountain early yesterday and I slept a good portion of the afternoon. So, I feel
So you recharged.
I recharged. for this
Okay.
week.
Are you ready for Wednesday?
No, but I will be after Tuesday.
Madison, you ready for Wednesday? Elias, you're Thursday? Damn, I wish I could be there. I don't think I'm gonna make it. Who else is here today that's doing that? Oh yeah, Greg, you ready? Someone? Okay. Everyone going? Right? Wednesday, support your fellow classmates? Tear them down a little bit? No? Come on, you guys gotta go. Yeah, see, Dawson will be there. You guys are in trouble now. Alright, so convergence. Obviously, we've created a model. It's a long process, right? Created this model, we've made through all the steps, we validated, we feel great about it, okay? So the results we're getting out, we feel decent about them. Well, now we want to make sure if we have something in which we want convergence, right? Now have results you feel good about, can refine the model to ensure you are at that accurate model level, right? Making sure it's at a reasonable accuracy. For members, this is not as big of an issue with convergence, right? Our derivation for our beam element is very close to the actual displacements, right? We have that third order, right, displacement, okay, that cubic. And so it's very, very close to exact. And so normally we don't split our members up. There are some cases we'll talk about in a second. Typical to model is individual elements of physical length, right? So if we have a girder that's 30 feet long, we would model one girder element that's 30 feet long and connect it at like beam to column intersections, right? So if it's a member in the real world, we would have it a member in our model. But the design may dictate further refinement. Like I mentioned P delta. If you looked out on VA, the help file in VA, right? We talked about how it's doing P delta, P big delta. How's it doing P big delta? Geometric stiffness matrix, right? So instead of doing an iterative approach, it's actually taking into account the fact that as it displaces, it messes up with the strain energy inside the member. And so it's just doing it in one step, right? If we're looking at P little delta, right? P little delta is the displacement over, right? This is the little delta. So if we had an axial load on a member, okay, this displacement, if we had a node at the front and or at the start and the end of this member, it's not going to consider P little delta, right? Because it doesn't know what's going on out here, right? It just knows where these two are at. So if these move, we're going to consider that, and that's P big delta. But if we have some displacement between these nodes, we're not going to consider that. And how do we consider that in VA? What's that? Break it up, right? We put it into a ton of little segments. We put some nodes out there. Now VA is looking at P little delta, and it takes it into account based on the fact that it's really looking at P big delta. And now we have all these members that are moving, right? Multi-story columns, right? We might want to refine our model. We had, say, 3 floors. We got a node here, we got a node here, we got a node here, and we got a node here, right? For a multi-story column, we might also want to do this P little delta, so we might want to throw in some more nodes along the length. We might also want to make sure that, right, we might want to split this member up into 3 members, okay? And that is based on the fact that we want to design this member later on in the design modules in VA. And we're not gonna get to that in this class, but when you do that, VA takes into account the length, right? And we talked about this a little bit last week with respect to our K values that we calculate, right? And so if even though this is a combined member, it might have some interior nodes. When VA goes to design this, it looks at the ends of the member. So it's gonna say that this column is 35 feet tall, and it's got some compressive load on it, right? Where in reality, it's braced at these 2 points. So you just have to be methodical about going through, and when you set up this column for design, you're gonna make sure everything is set up based on what VA is, or what you've modeled, okay? Also with interaction with other elements, we talked about this before, if you had a diaphragm that's sitting up here, right, and you only connected that plate at the ends of that member, then that plate is literally just connected at the ends of the member, and if they're not connected between, in order to connect it between, we're gonna wanna split up that member, right? So, we'll finish this.